In this section, we're going to cover density and pressure. Much of the macroscopic behavior of matter can be explained by the properties of the particles that make up a system. It is important to understand the microscopic properties of the three phases of matter. All matter is made of atoms. Atoms can combine to form molecules. How the atoms and molecules interact with each other determines the macroscopic properties of the substance. In a gas, the particles are able to move through space rather freely. The space between particles is very large compared to the size of the particles. The particles move until they collide with another particle or the walls of the container. A gas will take the shape of and volume of its container. In a liquid, the interparticle bonds are strong enough to keep the particles close together, which causes the liquid to have a definite volume, but the bonds are not strong enough to keep the particles arranged in a regular repeating pattern, such as in a solid. The particles are able to move past each other, but are not able to move far from each other, as in a gas. This causes the liquid to maintain a definite volume. The particles in a rigid solid maintain a close, fixed position relative to each other. This causes solid materials to maintain a definite shape and a fixed volume. In this unit, we are going to be covering some of the properties of fluids. A fluid is a substance that can readily flow. This includes liquids and gases, which we will cover. Plasmas, such as the substance that makes up stars like our sun, are also fluids, but we will not cover plasmas in much detail. Many fluid properties depend on the volume of the fluid. Volume is the amount of space occupied by a substance or object. There are several common units used to measure volume. A unit of volume can include any length unit cubed. The liter is also a common unit of volume. The mass density of a substance is the ratio of mass to volume. The equation for density is given here. The symbol that looks like a P is the Greek letter called rho. The SI unit for density is the kilogram per cubic meter. The density of gases will vary based on the volume of their container, because gases are compressible. However, liquids that are nearly incompressible. This means that a liquid's density generally depends on the type of liquid and not its container. This fact means that a measurement of a liquid's density can aid in the identification of an unknown liquid. The density of water originally defined the kilogram. 1 liter of water has a mass of 1 kilogram. In SI units, water has a density of 1,000 kilograms per cubic meter. However, it should be noted that water's density, like most other substances, is temperature dependent. Water has its greatest density at 4 degrees Celsius. When water is heated, it expands and therefore becomes less dense. It should also be noted that water is a unique substance in that when it is cooled below 4 degrees Celsius, it expands. Nearly all other substances do not share this property. This is why ice floats in water. In this example, I'm going to demonstrate how to convert units of density. To convert units of density, we're going to use the factor label method that you were taught in Physics 1. I'll start out by writing down the density that is to be converted with its units. I have to change the units in the numerator and the denominator. I will start with the numerator. A chart with all the metric prefixes is on the AP equation sheet. When using this table of prefixes, you will always put a 1 next to the unit with the prefix and the corresponding factor of 10 next to the unit without the prefix, like I have done here. We can then cancel units of grams. To eliminate cubic centimeters from the denominator, we will multiply by the conversion factor from centimeters to meters. However, you must remember to cube this factor to eliminate centimeters cubed. You can then multiply through, giving us our answer of 3,000 kilograms per cubic meter. To convert from kilograms per cubic meter to kilograms per liter, we simply have to multiply by the conversion factor 1 cubic meter per 1,000 liters. You can then multiply through, giving us our answer of 3 kilograms per liter. You could skip some steps if you remember that 1 gram per cubic centimeter is equivalent to 1 kilogram per liter. Next, I will introduce the quantity pressure. Pressure is defined as the ratio of force per area. This equation is on your equation sheet. The SI unit for pressure is the Pascal. The Pascal is defined as 1 Newton per square meter. The SI units for force and area. It is also common to express pressure in units of atmospheres. An atmosphere is the approximate average pressure from the atmosphere at sea level. An atmosphere is equivalent to 101 kilopascals or 101,000 pascals. In this example, we're asked to calculate the ratio of volumes of 2 cylinders. We can express that ratio as VB over VA. Then I substitute the formula for the volume of a cylinder in both the numerator and the denominator. Pi cancels. Then I can substitute in the expressions for the radii and heights of the cylinders. R squared cancels, and capital H cancel, leaving us with the answer 27. You should note that ratios are typically expressed as a number without units. Part B asks us to calculate the ratio of their densities. I can express this ratio as rho B over rho A. Then I can substitute the formula for mass density, mass divided by volume, for both the numerator and the denominator. The masses will cancel because the problem states that the cylinders both have the same mass. This leaves us with the inverse of the ratio that we found in part A, so the answer is 1 over 27. Part C asks us to calculate the ratio of pressure on the bottom of the circular face of each cylinder. We can express this ratio as PB over PA. I can substitute the formula for pressure, F over A, for both the numerator and the denominator. I can then substitute M times G for the force because the force on the bottom circular face will be equal to the normal force that the table exerts on the cylinder, which is equal to the weight of the cylinder. A whole bunch of things cancel, leaving radius A squared over radius B squared. Then I can substitute expressions for the radii and simplify the ratio to 1 over 9. There are some alternate units for pressure that I will discuss here briefly. However, it's unlikely that you will need to know any of these for the AP exam. The original unit for pressure was the torr, which was named after the inventor of the mercury barometer. A torr is equivalent to a millimeter of mercury, and we will discuss why this unit was used for pressure later when we discuss how a barometer works. Blood pressures are typically expressed in units of torr. A normal healthy blood pressure of 120 over 80 is 120 over 80 torrs. Here in America, where we're slow to change our units of measurement, we frequently measure pressure in pounds per square inch, or PSI. The pressure in your tires, for example, is almost always measured in PSI. It's important that we're able to explain macroscopic properties such as pressure with a consideration for the microscopic causes of those properties. We will cover this topic in much more detail next unit, but I'd like to mention it here that the pressure in a fluid is the result of the collisions of the particles of the fluid and the container or object upon which the pressure is exerted. The walls of the container or object must exert a force on the particles of the fluid during collisions. This force is always normal to the surface of the wall of the container or the object. Pressures are typically greater in denser fluids because there are more collisions taking place per unit time in a denser fluid. Pressure is typically greater at higher temperatures because the particles of the fluid are moving faster and therefore have more momentum and therefore require greater force from the wall of the container or the object. In this last example, we're asked to calculate the weight of the air in a room. We'll use the equation rho equals mass over volume. Then I will rearrange the equation solving for mass. Next, I can substitute the values for the density, length, width, and height of the room, and I calculate the mass of the air in the room to be 42.6888 kilograms. I can then calculate the weight of the air in the room using the equation m times g. I calculate this mass of air to weigh 418 newtons, and this is approximately 94 pounds of air. Part B asks to calculate the atmosphere's force on the floor of the room. We can use the equation for pressure, F over A. If I rearrange the equation to solve for force, I get pressure times area. Then I can substitute the value for pressure, remembering to convert to the SI units of pascals, and I can substitute the dimensions of the floor for the area. I calculate that the force of the atmosphere on the floor is 1.48 times 10 to the 6 newtons. I'd like you to think about why these two values are not the same number. Doesn't the floor need to support the weight of the air in the room? We'll discuss this question during our next Zoom meeting. In most everyday situations, objects and surfaces are exposed to pressures on two sides. In this situation, it is important to consider the net pressure force. This is caused by the pressure difference between the two sides of a surface. Be sure to watch the video demo to see a classic demonstration of the atmospheric pressure crushing a steel barrel. It can be shown that the net force on the surface is equal to the surface area times the difference in pressure. In our next Zoom meeting, we're going to consider these two questions. In an airplane, why is the cabin pressurized? And why are the airplane's windows so darn small? Why aren't they bigger, like the windows on a bus? See you next time.